Welcome student, myself Dr. Barnali Bej from Department of Chemical Engineering, Haldia Institute of Technology. Today's topic is energy balance, introduction, enthalpy, heat capacities. In this lecture, I'll discuss the basic of energy balance and enthalpy and heat capacities. First of all, we need to know the importance of energy balance. Why we need to do energy balance in chemical engineering. In general, a huge quantity of energy is consumed in every chemical process industries. Efficient and proper conversion of fuel resources into energy and proper utilization of energy in operation of the plant are the major two concern in chemical engineering. Now, energy balance are carried out in chemical process industry for doing several tasks. Number one, for choosing proper operating conditions to reduce loss of energy. Number two, for doing appropriate design of waste heat recovery system. And number three, for finding out energy requirement for heating and cooling of a process. Therefore, all these suggest the possible means for the conservation of energy. Energy balance basically based on the law of conservation of energy. Law of conservation of energy states that although energy may be converted from one form to another form, it cannot be created or destroyed. Whenever uh, one form of a quantity of one form of energy is produced, an exactly equivalent amount of another form of energy must be used up. Now we will discuss the components of energy balance equation. The primary component of energy balance equations are heat and work. Energy expended in the form of work. Further, mechanical work is converted to the heat energy, which is measured by the increase in temperature. And heat and work represent energy in transit. Then the important components of energy balance equation are kinetic energy, potential energy and flow energy. Potential energy possesses the energy into the system due to its position above some reference level, and kinetic energy it due to the its motion. And flow energy is in the flow process some fluid element possesses some additional energy due to the pressure of the fluid. And another important component of energy balance equation is internal energy. Internal energy is the energy stored in the system by virtue of its configuration and motion of the molecules constituting the system. In a cyclic process, the internal energy of the system remains same even after a series of changes. The internal energy is a state function. It does not depend on the path in which path the changes occurs. In non-cyclic process, heat and work involved are not same. In non-cyclic processes, some amount of energy is stored within the system, or some amount of energy or some amount of stored energy is released from the system. So there is the change in stored energy, and the change in stored energy is measured as change in the internal energy of the system, and that is represented by the change in internal energy, that is delta U equal to Q minus W. It is the mathematical form of first law of thermodynamics. Delta U is the change in internal energy, Q is the heat added to the system, and W is the work done by the system. Now another important component of the energy balance equation is enthalpy. To describe enthalpy, we will consider two systems, the system at constant volume and the system at constant pressure. Now first we consider the system at constant volume. When the system is at constant volume, then there will be no work done. That means the system is unable to do work. So W equal to 0. And so total heat added, the amount of heat added to the system, that is totally utilized to change in internal energy change. But when the system is kept at constant pressure and it is free to move or free to expand its volume, then the amount of energy, amount of heat supplied to the system is not equal to the change in internal energy of the system. Some part of the energy or heat supplied to the system is utilized to occupy the new volume, or it utilized to work for expansion of the system. So heat supplied at constant pressure can be measured as the change of another thermodynamic property of the system, that is called enthalpy. Enthalpy is denoted as H. H equal to, it is represented as H equal to U plus PV. U, P and V all are the state function, so H is also the state function. So basically enthalpy of the system is the total energy including internal energy of the system plus the energy required for its expansion to occupy the new volume. Now the equation 2, H equal to U plus PV, we can write in differential form dH equal to du plus dPV, and on integration delta H equal to delta U plus delta PV. Now equation 3 can be expanded as dH equal to du plus PdV plus VdP, and it can be rewritten as du, replacement of du as we know from the first law of thermodynamics, du equal to dq minus dw. So we can write in place of du dq minus dw plus pdv plus vdp, and again pdv equal to dw, pdv equal to dw for constant pressure, pdv equal to dw. So and constant pressure process dp equal to 0. So the equation 5 reduces to only dh equal to dq. So dq, that is heat added to the system at constant pressure process, is equal to the change in enthalpy of the system, provided the system at constant pressure. For constant volume process, W for expansion will be 0. So the equation 5, and from the first law of thermodynamics, du equal to dq. So heat added at constant volume process, heat added will be equal to the change in internal energy. Now heat capacities. Heat capacity is defined as the amount of heat required to rise the temperature of 1 degree. It is represented as amount of heat dq, dq equal to C dt. C is the heat capacity of the substance. And specific heat capacity is heat capacity of unit mass of the substance. That is called specific heat capacity. Now heat capacity are two types, heat capacity value at constant volume and heat capacity value at constant pressure, that is Cp, and heat capacity of at constant volume is Cv. Now heat is supplied to a system at constant volume. So heat supplied dq equal to Cv dt, and Cv is the heat capacity at constant volume. So Cv equal to del Q by del T at constant volume. Now we know from the previous um, description, dq equal to du at constant volume process. So Cv equal to del U by del T at constant volume. That is equation 6. Heat is supplied to a substance at constant pressure. So heat supplied dq will be equal to Cp dt. Cp is the heat capacity value at constant pressure. So Cp equal to del Q by del T at constant pressure. Now for constant pressure process, we already know dq equal to dH. So Cp equal to del H by del T at constant pressure. Heat capacity of substance is not constant. It varies with temperature, and it is expressed as polynomial equation of the temperature, variable temperature. So it is expressed as Cp equal to A plus Bt plus Ct square, where A, B and C are constant, which are determined by standard method of curve fitting. Now the change of enthalpy in constant pressure process between the temperature range T1 and T2, and it is expressed as enthalpy change delta H equal to integration T1 to T2 Cp into dt, and it can be rewritten as integration T1 to T2, and by replacing Cp, the polynomial equation, A plus Bt plus Ct square whole dt. Now if we have the heat capacity value with the temperature from the experimentally determined result, then we can plot the heat capacity value versus temperature, and enthalpy change is determined by the graphical integration by calculating the area under the curve between T1 to T2. Now mean heat capacity. For calculating heat interaction and enthalpy change of gaseous system, mean heat capacity at constant pressure in the temperature range is useful. So mean heat capacity is expressed as Cpm, and Cpm, mean heat capacity, is equal to Q by T2 minus T1, and that is equal to integration T1 to T2 Cp dt by T2 minus T1. So again we can write 1 by T2 minus T1 integration T1 to T2 A plus Bt plus Ct square whole dt. So after integration and by putting the limit value T1 and T2, we can get the mean heat capacity of the gaseous substance. Mean heat capacity is evaluated between the given temperature and a reference temperature Tr. For calculation of enthalpy changes, the use of mean heat capacities is limited to temperatures lying between given temperature T and Tr. The heat required to heat a gas from T1 to T2, and if Tr, the reference temperature, is outside this limit, then heat required to heat the gas will be equal to Q1 minus Q2. That means the individual heat required with respect to reference temperature. given temperature and reference temperature. We have to subtract this individual heat required. So this equation can be rewritten as CPM1 T into T1 minus TR minus CPM2 into T2 minus TR. CPM1 and CPM2 are the mean heat capacity value at given temperature T1 and T2 respectively. Now we will solve one problem to find out the mean heat capacity of the gaseous substance. Now the problem statement is given. The molar heat capacity of carbon dioxide gas is given by Cp equal to the expression. Cp expression is given, where Cp is in kilojoule per kilomole Kelvin and T is in Kelvin. Calculate the following. Number 1, the mean molar heat capacity between 500 to 1000 Kelvin, and number 2 is the heat required to raise the temperature of 200 meter cube per hour of gas, carbon dioxide gas at STP from 500 to 1000 Kelvin. Now the solution is, first you have to find out the mean molar heat capacity. So we will apply the equation mean heat capacity CPM equal to 1 by T2 minus 1 by T2 minus T1 integration T1 to T2 A plus BT plus CT square whole dt. Now after integration and putting the limit value, we will get the final equation 1 by T2 minus T1 into A into T2 minus T1 plus B by 2 T2 square minus T1 square plus C by 3 T2 cube minus T1 cube. Now we know the all values of A, B, C and the temperature range given. T1 is 500 Kelvin and T2 is 1000 Kelvin. So by putting all the values, we will get the mean molar heat capacity. And it is evaluated 50.03 kilojoule per kilomole Kelvin. Now the second part, the heat, you have to find out the heat required to raise the temperature of the 200 meter cube per hour carbon dioxide gas. Now the volumetric flow rate is given, carbon dioxide volumetric flow rate is given, and it is at STP. So we all know that at STP 1 kilomole of any gaseous substance occupies 22.4 liter volume. So 200 meter cube divided by 22.4, it will give the kilomole, it will give the moles at STP condition. So it will come 8.928 kilomole per hour. Now we can find out the amount of heat to be supplied to raise the temperature from 500 to 1000 Kelvin. So M will be mCp dt. M into CPM, the mean heat capacity and temperature difference. So moles of gas to be heated multiplied by mean heat capacity of gas into temperature difference 500. It will come 22.34 into 10 to the power 5 kilojoule. So in this problem, we will learn how to calculate mean heat capacity and heat requirement to heat the gaseous substance at within the given temperature range. Now the second problem, it is related to the calculation of mean heat capacity with respect to reference temperature and heat required with respect to reference temperature. Calculate enthalpy change for 1 mole of a gas when it is heated from 400 Kelvin to 1500 Kelvin at 1 atmospheric pressure, given that the mean specific heat of the gas at the reference temperature of 273 Kelvin are 35 kilojoule per kilomole Kelvin at 400 Kelvin and 50 kilojoule per kilomole Kelvin at 1500 Kelvin. Now the reference temperature 273 Kelvin is outside the range, given range 400 and 1500 Kelvin. So the amount of uh, heat or enthalpy change delta H, enthalpy change, that is delta H 400 to 1500 Kelvin, it is obtained by differentiating the amount of two enthalpy between the lower temperature range with respect to reference temperature and higher temperature range with respect to reference temperature. So it is obtained by calculating delta H 1500 to 273 Kelvin and subtracting, that is minus delta H 400 to 273 Kelvin. So it is rewritten as CPM2 into T2 minus TR minus CPM1 into T1 minus TR. And by putting all the values given, we can get the result, and it will come 56905 kilojoule per kilomole. So enthalpy change is calculated. So up to this we will learn today. Thank you.